Good morning, everybody, wherever you're listening from, and welcome to these summer lectures that will hopefully introduce us to the latest advancements of on-chip interconnection networks. And we will oscillate between emerging use cases and applications and the unmatched potentials of emerging interconnect technologies. My name is Davide Bertozzi, and I've been leading the multiprocessor system on chip research group at University of Ferrara in Italy since 2004. Well, in this introductory lecture, I will review some fundamental aspects of network on chip design, but not in a standard tutorial way. Rather than depth, my focus will be rather on breadth. I will go over the historical trajectory of NoCs from a research concept into a technology of practical relevance. And I will use representative use cases to better understand what happened. At the same time, I will try to establish correlations between historical research questions and the methodologies that were used to answer them, and current research questions and working methodologies. And the reason is because the past teaches us what to pay attention to in the present, what is fundamental and what is not for the future, what was wrong and what was not, and prompts us to effectively tackle emerging technical challenges in the present. In particular, I will cover an extensive early research framework for topology selection, demonstrate its unchanged relevance today, and correlate it to the current topology-related research. In fact, today, people are still researching topologies, and they are researching them to bring system integration to the next step. I'm talking about the current integration challenges for 2.5D integration and 3D stacking. Similarly, I will demonstrate the strategic role the routing mechanisms had at the beginning of the network on chip era and today for the sake of cybersecurity. Finally, I will try to learn some lessons from the early cross-benchmarking initiatives of on-chip interconnection networks with communication buses that were state-of-the-art at the time where NoCs were introduced. And this is still relevant today because today we are facing a new cross-benchmarking challenge, if you think about it, because we are trying to make the case for interconnection networks built on top of emerging technologies. In this case, we can learn from the past what to care the most when assessing an emerging interconnect technology, such as, for instance, silicon nanophotonic networks. In the end, I will show that unlike the early days, network on chip research is not an isolated discipline anymore, but rather it's a barrier-breaking discipline. Because today there is the trend to co-design networks on chip with the system architecture, with the system software, and with applications as well. Okay, I think we are ready to start this journey. I hope it will be exciting for those of you who have the patience to follow me till the very last lecture in mid-July, and who prefer learning about NoCs rather than going to the beach or hiking. I think it's a tough choice, it's a challenge, but it's great if you're going to have fun just the same. Regarding questions, so there is a Q&A section in this streaming tool, and we will use that facility. So if you have questions, please post your questions there. I will not answer questions immediately, but let's say more or less after 1 hour, I will stop. There will be a break. During the break, I will review the questions, select the most representative ones, and we'll try to answer them live right after the break. Okay, so this is the methodology that I'm going to follow. So please feel free to post your questions to the Q&A section of this site, and then I will answer them later. If there are some questions that remain not answered, please feel free to send an email to me, and I will answer offline. So one thing that we know for sure is that in these lectures, we are going to talk about networks on chip, okay? That's for sure. Network on chip, or NoCs, have gone all the way from a research concept into industrial application into a relatively short time frame, roughly 10 years. And this is an uncommonly short time for an emerging technology to make it all the way to application. This was possible because NoCs were providing an effective means of coping with daunting challenges posed by technology and by system-level designers. In fact, technology was increasingly becoming a sort of threat to design convergence, and not only a source of opportunities for boosting performance and for reducing power. Especially wire delay was not scaling like gate delays. In contrast, it was degrading as the feature size was shrunk, which today we call the reverse scaling of interconnect. As a result, dealing with routing congestion became a nightmare for all physical designers, and communication architectures were required to be layout friendly from the ground up. At the same time, in the early 2000s, system on chip started to heavily rely on multi-core parallelism. This called for more scalable and higher bandwidth communication fabrics with respect to state-of-the-art communication architectures consisting of shared buses, crossbars, multi-layer architectures. Moreover, the complexity of leading-edge SoCs combined with the ever-increasing time-to-market pressure was pushing for a strong componentization and modularization of silicon platforms in order to reduce the design effort and improve the design productivity. Last but not least, the globally asynchronous, locally synchronous paradigm became mainstream because it enables fine-grained power management, and it enables to bring together cores that belong to independent voltage and frequency islands, and cores that are heterogeneous in terms of the parameters they are instantiated with. So the point is that network on chip meet all the key requirements imposed by these converging trends. Actually, they met all these key requirements, and they currently still meet all these key requirements. Because if you think about it, they facilitate to construct a multi-core or many-core architectures in a modular way. They are bandwidth-rich communication fabrics, and today maybe they are not bandwidth-rich enough. They provide communication abstractions and services across component boundaries. It means that although you are instantiating heterogeneous components, you can ask for communication services across the heterogeneous end-to-end platform. They enable the top-down design of highly power manageable, globally asynchronous, locally synchronous architectures, and they enable segmented interconnect design. They split the global interconnection system into segments, and these segments are highly predictable in terms of the performance they can deliver. They are highly predictable in the face of the technology, which poses delay challenges, delay variability challenges, and exhibit a lot of path redundancy. Therefore, this communication architecture is not the single point of failure for the system anymore. So the first position papers on networks on chip date back to the early 2000s. In 2001, Bill Daly and Brian Toles from Stanford University published a paper with an instructive title, Route Packets, Not Wires. The idea was to let the system module communicate by sending packets to one another over an on-chip interconnection network. Shortly afterwards, maybe in parallel, but from the publication viewpoint shortly afterwards, Luca Benini and Giovanni De Micheli published a paper. The title was Networks on Chip, a New System on Chip Paradigm. And this was more on the methodological aspects of network on chip design. In fact, they were proposing a layered design methodology of micronetworks as the only path to mastering the complexity of future system on chip design. So this idea of interconnection network was not new, since interconnection network were already used for off-chip communications, for instance, in computer clusters, but under radically different trade-offs. For this reason, the milestone books in this research field target the design principle of interconnection networks in general, and there is nothing specific about networks on chip. José Duato in 1997 published a book where he was giving a coherent and comprehensive treatment of the field with very rigorous and formal statements of concepts, classifications, tariff classifications of design choices. And it was an attempt to provide a unified view to structure the knowledge on interconnection networks. In 2003, Bill Daly came out with his own book that, in addition to documenting and presenting the key concepts and research findings, provided an incisive practical treatment combining the theory behind NoCs with the practice of building them. So it had a more practical attitude toward the field. There is no doubt that early network-on-chip architectures were directly inspired by off-chip interconnection networks. As you can see in this table, there is a list of early network-on-chip solutions. And now we don't have time to zoom into the parameters of the different proposed architectures, but you can see that early topologies that were proposed directly borrow from the off-chip interconnection network domains. For instance, FAD3 topologies, multidimensional topologies have been proposed. There were buffering schemes that implied quite a lot of buffering, such as, for instance, virtual output queuing. There were switching strategies that are very nice and simple to treat, such as virtual castle switching, but that come with large buffering overhead in a chip environment. Then we had some flow control protocols that are not completely matched to a chip environment, such as the HiPEAC flow control protocol. There were adaptive routing strategies, and there was, above all, poor emphasis on the interfacing aspects. But for system-on-chip design, having standard socket interfaces in such a way that you can plug your component into the system using a standard interface is fundamental, is of fundamental importance. However, researchers soon understood that network-on-chip design is unique and profoundly different from off-chip interconnection networks, because in an on-chip environment, you have tighter research and power budgets. Therefore, the design choices that you typically follow for an off-chip interconnection network, they do not hold anymore in an on-chip environment. And as a result, researchers spend quite a lot of time to retarget the design point for interconnection networks for an on-chip environment and for the distinctive challenges of this environment. So the network on chip becomes a discipline in itself. And therefore, new books start appearing that are dedicated exclusively to the on-chip realization of interconnection networks. Let me mention Benini and De Micheli's book in 2006 that highlights the design principles of on-chip interconnection networks and presents early stage architectures. This book was trying to give a structure and a unified view to key research findings, but it was doing that in a fast evolving field. Therefore, some of its technical content is currently outdated. In 2010, myself and José Flitsch from Polytechnic University of Valencia, we tried to provide a one-stop source for the interested reader, and we were trying to put together in a book design principles that at that time were starting to consolidate. The field tended to stabilize, therefore it was about time to come up with a book. And I would like to say that because of the time this book was written, its technical content, it's today still recommended for people that want to get ready for network on chip design and research as soon as possible. Okay, so now I will try to provide a relevant example of what happened in the early days of network-on-chip design, where inspirations coming from off-chip interconnection networks had to be tested in an on-chip environment, and proper design points for an on-chip environment had to be worked out. And the most interesting case study certainly has to do with topology selection. And we will see in this presentation that this is not just history. This has current relevance, and there is today a follow-up. So please follow the entire story. So at the beginning, the bidimensional mesh, you can see here an 882 mesh, therefore a bidimensional grid of routers, and you have a computation tile attached to its router, and you have 2 dimensions, and you have 8 switches in each dimension. So you have along the X dimension and along the Y dimension, you have 8 switches. So in short, I will call this architecture the 2D mesh. So the 2D mesh at the beginning was regarded as a purely academic solution, while more fancy topologies existed, and they were actually investigated and tried out with the claim of a higher practical and industrial relevance, because many topologies exist that in principle can do much better than a 2D mesh. A proxy for the peak throughput of a topology, so if you want to evaluate the peak throughput of a topology without too many simulations, there is a proxy for that, which is the bisection bandwidth. Therefore, you draw a line that cuts the topology in 2 symmetric parts, and the links that are cut by this straight line, they are called the bisection cut, and the sum of the bandwidth of the links on the bisection cut is called the bisection bandwidth. So it's the bandwidth that flows throughout this section of the network. Well, many solutions provide better bisection bandwidth, therefore potentially better peak throughput than a 2D mesh. For instance, the so-called C-mesh topology. So the basic idea of the C-mesh topology is fundamentally to exploit these boundary switches. These boundary switches have, in a 2D mesh, fewer ports than the switches in the middle. The switches in the middle in a 2D mesh have 4 connection ports to the north, south, east, and west directions. In a C-mesh topology, the boundary switches that in principle have a lower amount of ports, such as this switch has originally only 2 ports to the south and to the east. In this topology, you add express links exactly along the periphery of the topology, in such a way that also the boundary switches have the same number of input-output ports, and you can use these express links that have been added along the periphery of the topology to improve the bisection bandwidth. You can see that if you draw the same straight line here, you end up cutting not only the links of a standard 2D mesh, but additional links at the boundary. It means that this topology is in principle capable of carrying a higher peak throughput with respect to the 2D mesh. Another promising solution is the family of multidimensional topologies. So in multidimensional topologies, you have, as the name says, more than 2 dimensions, such as in this case, you have, it's difficult to figure it out from the drawing because it's difficult to draw it, but you have 6 dimensions, and compare it to the 2D mesh where you have only the X and Y dimension. Here you have 6 dimensions, and along each dimension, you have only 2 switches. So this is called the 286 mesh. It's a 6-dimensional mesh topology. And we have other variants, such as topology that have a lower amount of dimensions, such as 3 dimensions, like in this case, but they have more switches along each dimension. You can see that in this case, you have 3 dimensions and 4 switches along each dimension. You can see here a block of 4x4 switches, and these blocks are connected with each other. Overall, if you count them, there are 3 dimensions. Clearly, the nice property of multidimensional topologies is that with a single, look at here, with a single network hop, you can go far away. Okay, so you can cover multiple physical hops in a single network hop. Therefore, they all promise of low latency communications. Another extensively investigated family of topologies is the fat tree. In fat trees, you can see that you have all the nodes logically represented here on the left-hand side. And in order to enable communication from this node to this node, you just need to reach the common switch ancestor before being derouted downwards. As you can see, this is an ultra low latency topology. And you can have some topology variants. And because of their low latency and high bisection bandwidth, these topologies have been considered extensively in the early days of networks on chip, but then they never took off because they are very difficult to lay out on the bidimensional silicon surface, because they have, you can see here, quite intricate wiring, and this is not, I would say, compatible with a layout-friendly topology for the bidimensional chip surface. Last but not least, especially industry had a lot of interest in this kind of concentrated topologies. So what's a concentrated topology? It's a topology where you try to connect multiple cores, like in this case, 4 computational tiles, to the same switch. Okay, so in this case, what happens is that you can instantiate a lower amount of switches overall. Compare these with the standard 2D mesh. You have much lower amount of switches, so lower amount of resources, which also means that you are going to have a lower latency, because the number of hops to go from a source to the destination on average is much lower than the standard 2D mesh. And because of this feature, industry was extremely interested in this kind of topologies. But what we need to take into account is that in this kind of topologies, you have a lot of switch input-output ports, because not only, for instance, for this switch, you have 4 connecting links to the neighboring switches, but you also have 4 input-output links to connect to the cores. Therefore, here, switches have a so-called degree of 8, so 8 I/O ports, while in a standard 2D mesh, the switch degree is 4. And we will see shortly afterwards that this has implications. However, early works were not taking into due account the silicon substrate. And the silicon substrate is key in order to assess the ultimate performance and power characteristics of all these topology variants. When we consider a semi-custom design flow based on standard cells, it becomes apparent that, as you can see in this plot, when you try to draw the maximum clock speed of a switch as a function of the number of input-output ports of this switch, from a 2x2 switch to a 30x30 switch, it's clear when you synthesize it, you place it, and you route it on your technology library, what you find out is that the maximum operating frequency decreases substantially. Therefore, if you have a 22x22 switch, you can hardly achieve 200 megahertz in a 65 nanometer technology. And if you are limited, let's say, to a 5x5 switch, the operating speed is somewhere around 900 megahertz. And here there are multiple lines. I don't want to go into the details, but when the dashed line stops, it means that it's not possible to have design convergence for these high radix switches. And the reason is because for more than 22 ports, the synthesis and place around tools are not able to meet the stringent timing requirements are not able to meet the design rule constraints of the technology at hand, and they are not able to alleviate crosstalk concerns. Therefore, the design simply fails, simply does not converge. So that's the reason why high radix switches were never successful for on-chip environments unless you revert to full custom design. That's a different story. So what are the implications for our topology? If you consider the 2D mesh, post-synthesis, the maximum operating speed is more than 1 GHz, because you have fundamentally 6 input-output ports, 6 ports because here you have 4 ports for connecting to the neighboring switches plus 2 ports to connect to the local computation tile, 1 for the processor core and 1 for the memory. But a 6-dimensional topology has 8 I/O ports because of the large number of dimensions that it has, and therefore it ends up running at 950 megahertz post-synthesis. So you can clearly see that right from the beginning, there is an imbalance, okay? So the topologies that instantiate a higher number of I/O ports are going to run slower than other topologies. So after all, the 2D mesh is not that bad, but there are further implications. At some point, if the link is going to be, let's say, larger than a few millimeters, what happens is that the critical path, so what determines the clock speed of the topology, is not the switch anymore, but it is rather the link. And we perform this experiment. On the x-axis, I'm presenting the link length between any 2 neighboring switches, and on the y-axis, the maximum clock speed that can be achieved. And the experiment was performed for a 65 nanometer technology and a 45 nanometer technology. As you can see, let's just take a look at the 65 nanometer technology. As you can see, as you increase the link length, the maximum achievable clock speed decreases. And decreases significantly till you get a saturation effect. A saturation effect is around 100 megahertz, more or less. And the reason is because the link becomes longer. The synthesis tool has to put a lot of buffering on it in order to keep up with the timing constraint. But in the end, it ends up instantiating too many buffers, and it starts degrading the delay of the link itself. And at the same time, the link becomes extremely power consuming. And if we repeat the same experiment for a 45 nanometer technology, what you find out is that the absolute value of the clock speeds are lower. They are surprisingly lower. And the reason is because while gate delays scale very nicely, very smoothly with the scaling of the feature size, for the interconnect, the opposite holds. We talk about the reverse scaling of interconnect. It's like having a pipe, and it's like reducing the cross-section of a pipe. Clearly, the amount of water that can flow through the pipe per time unit is lower. The current is lower. Therefore, scaled interconnects suffer from degraded delay. So what are the implications of this? So the implications are the following. The 2D mesh has, in this case study, 1.5 millimeter long links, sorry. And the 6-dimensional topology has links that in the worst case, in the highest dimensions, are 7 millimeters, which means that the maximum clock speed that we were able to achieve post layout was 890 megahertz for the 2D mesh and 220 megahertz for the 6-dimensional topology, which fundamentally means that the 6 mesh is not usable because 200 megahertz, nobody will ever instantiate something like this. There is clearly something that you can do to restore performance. We call this link pipelining, okay? This is still a very current performance optimization technique of network on chip links. But let's pay attention. What does it mean to pipeline the link? It's like when you go to the freeway and you have gas stations. You can refill your tank and start for your journey again with the tank, which is as full as it was at the beginning, right? That's to use an analogy. Link pipelining means to retime your link in such a way that you can change a very long link delay into a multi-cycle latency. So before applying link pipelining, you can cross the link in one cycle, but one very slow cycle. After link pipelining, maybe it takes 3 or 4 cycles to cross the link, but the clock period is much shorter. So in the end, maybe if you count the total absolute time to cross the link, it turns out hopefully to be smaller, and the throughput is at the same time amplified quite significantly. So now we need to pay attention to one detail which is typically overlooked. Retiming a link doesn't mean only to put a register along the link. Doesn't mean to break a link with a register. Because in a network on chip, we also need to handle flow control. Flow control means that if you have here a source and you have here a destination, it means that you should fundamentally prevent the receiver buffer from overflowing. And one way to do that, one simple way to implement the so-called back pressure of flow control is to use a stall signal, as it is actually represented here. So you have here a stall signal, and the stall signal means that the current data has not been sampled yet because the buffer is full. When you get a stall signal, this pipeline stage that has an internal final state machine should fill up all its buffers, and once all the buffers are full, it should propagate the stall signal upstream. So because of the need to handle flow control, a pipeline stage is not a single register, but it is at least a couple of registers, a multiplexer, and the final state machine. So it's something which, you know, it's not that simple as we were expecting it to be. Why do we need at least 2 registers? The reason is here. So this is a pictorial representation of this circuit here, okay? And you can see how it works, what its operation. So you have, let's call it now packet A and packet B. You are transmitting A to the receiver. Then the receiver becomes full and it activates the stall signal, which means that packet B has not been received yet. So we need to store the packet that was in flight at the time we got the stall, which is packet C. So we need the backup slot here. We need a second register to store C, otherwise C gets lost. At the same time, we propagate the stall signal upstream, and the situation remains frozen in this state. Then you get a go signal, and when you get the go, it means that B has been sampled, and then you can resume transmission in the same way that it used to work at the beginning. So we are again in the same state of the beginning. For this reason, I think that I was trying to convince you that a pipeline stage is not as simple as a single register, but it's much more than that. So what about pipelining our topology? And in particular, pipelining our 6-dimensional mesh, because the 6-dimensional mesh has a speed which is 200 megahertz, 220 megahertz. So the one possibility would be to apply link pipelining to the dimensions higher than the second one. Because if you want to compare this with the 2D mesh, the 2D mesh is 2 dimensions, and we don't want to apply link pipelining to 2D mesh. And so we apply link pipelining for fairness to the 3rd, 4th, 5th, and 6th dimension of this 6-dimensional topology. And it finds out that in order to sustain a final operating speed of roughly 900 megahertz, you need to apply one pipeline stage to dimension number 3 and 4, and up to 5 pipeline stages for dimensions 5 and 6 because they correspond to the longest links in the topology. So after link pipelining, we have a decent speed for this topology. So the topology comes back to life again, right? So you cannot use it, you cannot instantiate it because it has a quite good operating speed. But now I will try to demonstrate that this pipelining did not come for free, but it came at a huge implementation overhead. So what happens if you try to instantiate these topologies, such as a 2D mesh and a 6-dimensional topology, in an 8x8 multi-core system, and we apply some synthetic traffic benchmarks to this multi-core system. In this plot, we report for several topologies and for several traffic patterns, we report the normalized throughput, the normalized peak throughput of these topologies with respect to the 2D mesh. So it means that if the value is lower than 1, it means that the 2D mesh performs better. If the values of these bars are higher than 1, it means that these topologies are performing better than the 2D mesh. So if you do not apply any pipelining, as you can see here from the red bars, there is no competition. The 2D mesh is the absolute best topology. And this is because these other fancy topologies have overly long links, or they have an overly large number of input-output ports. And this is too bad because it translates into a low operating speed. And it fundamentally means that the peak throughput sustained by this topology will be very low. Instead, if you apply link pipelining, we can see that most, not all, but most of these topologies perform better than 2D mesh. These are the blue bars, okay? And this is what people were expecting, right? So these topologies have better theoretical abstract properties than a 2D mesh. And here we are exactly capitalizing these properties. The performance, the peak throughput sustained is better. Okay, but now the question is, what was the cost for this? For that, was the cost, the implementation cost, proportional, disproportionate, or what? And in order to figure that out, I now plot a ratio: peak throughput divided by instantiated area. And this metric tells us what is the efficiency of the instantiated area, okay? So to what extent the instantiated area translates into performance speedups. So you can see from this plot that now almost no topology is above 1, which means that the performance speedup that they provide comes with a disproportionate area cost, okay? So link pipelining was so aggressive in order to bring them up to speed that overall the throughput area ratio suffers a lot. And you can see that there are some exceptions to that. For instance, the 6-dimensional mesh, which was the absolute best when you consider the performance. Now, when you consider the area efficiency ratio, you can see that only in one case it's above the 2D mesh. And also the 4-dimensional mesh, only in one case. So it means that for a specific traffic pattern, it's worth using, but in general, it's not worth using. I mean, it has a disproportionate cost. Then it's up to you. If you want to use it, feel free to do that, but you are aware of the fact that it comes with a huge cost. And it's not only about the instantiation of pipeline stages. It's not only about that, but it's also because when you instantiate a pipeline stage and therefore you enable your topology to be operated at a higher speed, you need to re-synthesize your switches for the higher speed. And therefore, if your switches have a higher number of I/O ports overall with respect to the 2D mesh, which is the case in multidimensional topologies, then you have an amplifying effect of the area overhead, because you are resynthesizing a huge number of I/O ports for a higher operating speed, which means that the instantiated area by the synthesis tool will be higher. So what is the key takeaway? The key takeaway from the early days of NoC, and we can still see this in current products, in current NoC applications for general purpose systems, is that the 2D mesh was and still is the reference topology. In some cases, you have some optimized variants, and the most popular one is the folded torus. The folded torus, the torus is a topology that has wraparound links with respect to the 2D mesh, and there is a nice way to re-engineer the layout of a torus, which is called the folded torus, that makes this topology layout aware. But these are the most popular topologies for on-chip realizations when it comes to general purpose regular systems. For application specific systems is a different story, and we will see it afterwards. Okay, so why I went through this? So first of all, to provide some background for the people that approach this topic for the very first time, but also to link this with what's going on today. Because today, it's quite interesting to note that topology research is again on the rise. In fact, the end of the Dennett scaling and the slowdown of the Moore's law are causing a surge of interest in new system integration technologies. And this is because the demand for computational power from applications is ever increasing. It's not going to slow down like the Dennett scaling rule or the Moore's law. Okay, the request for computational power keeps increasing. And although for quite some time we have been debating about the pros and cons of advanced integration technologies that are there in the market, such as 3D stacking, but 2.5D integration has gained immense popularity in industry and wide applicability in light of its milder pressure on the manufacturing process. The basic idea of 2.5D interposer-based integration is that you can integrate multiple discrete chips that are also called chiplets within a package over a silicon interposer, although other packaging options exist. As you can see here, you have on a common substrate, which is a silicon interposer, you have the integration of 3D stacks of DRAM dies. So this is 3D stack and main memory. And you have also chiplets that integrate the processing cores. So you can see in this picture a way to disintegrate a monolithic many-core processor into a chipletized many-core processor. So a many-core processor which is split into several chiplets, and these chiplets are mounted, are integrated together on top of a silicon interposer. So let's approach these kind of systems from the viewpoint of the communication architecture. So while obviously chiplets have their own interconnection network, so locally each chiplet has its local network on chip, also the interposer comes with may come actually with its own interconnection network. And this overall gives rise to a hierarchical interconnection system. But you should also consider that the interconnection network that you lay out on the silicon interposer may be different or may come with different parameters with respect to the interconnection network that you have on the chiplets. Therefore, this is nothing else but an heterogeneous hierarchical interconnection system. So chiplets, as well as interposer, have their own interconnection network with different parameters and operating conditions. So this is a new environment. And there are new research questions that arise in this environment, actually quite a lot of them. First of all, what is a suitable granularity for processor chipletization, for processor disintegration into chiplets? At which granularity you should do that, if you want to do that at all, right? You need to also understand that. Moreover, if you do that, which topology are you going to use to connect the chiplets with each other and with the main memory on the silicon interposer? Because while the theory of topologies for the chiplets is kind of consolidated, as I've shown you in the previous slides, but no, what kind of topology to use on the silicon interposer is not obvious at all, and as we will see shortly afterwards. In addition to that, there are many other questions that are outside the scope of this presentation in terms of routability of the system, composability, yield, thermal control, cost, synchronization concerns, and so on. So let's now apply the first lesson learned at the beginning of this lecture. And the first lesson is that before selecting a topology, you should understand the target environment. You can reapply the concept that you're borrowing from a different context into a new context. You need, first of all, to understand what are the distinctive features of the new context in order to understand what is the best embodiment of the networking context in the new environment. So, first thing is to answer the following question: does it make sense to disintegrate monolithic processors at all? A paper from Nathalie and Reitjerger's group in 2015 tried to bring some quantitative evidence of the fact that disintegration actually makes a lot of sense. The main reasons are because if you break your chip down into smaller chiplets, you can fit many more of them in a wafer. Therefore, you suffer less for the mismatch between the chip rectangular shape and the rounded periphery of the wafer. At the same time, if you assume a predefined defectivity pattern, as it is shown in this picture, for the wafer as a whole, you end up affecting a lower amount of chiplets if you keep their size small. Therefore, you end up lowering your yield loss with respect to having big chiplets. So this consideration seems to play in favor of disintegrating many core processors into small chunks, into small chiplets. As a result, yield and cost are fundamental design goals for interposer design. There are other considerations that will be made in the following slide about how small these chiplets can be or make sense it to be. But for the time being, let's think about this. In this domain, key design goals are yield and cost, because the interposer is a single point of failure. So if there is something that goes wrong in the interposer, and especially in the logic that you implement on an interposer, then you have to throw away the entire system. And it's quite a lot of money that gets lost. And for this reason, many interposers today, from a commercial viewpoint, they are passive. That is, they implement no devices, only routing of signals between the chiplets and from the chiplets to the memory and the other way around. Alternatively, interposers may be implemented in an older process node with respect to the chiplets, because older process nodes are more mature and they exhibit lower defectivity. And therefore, we understand that packing devices on the interposer to the same extent that you pack them on the chiplets doesn't make a lot of sense, because it increases the critical area, that is the vulnerable area, the area that becomes susceptible to defects, and this is going to affect yield and cost. Therefore, today, there is some agreement in the open literature about minimally active interposers. So you should try to minimize the amount of logic that you implement on the interposers as much as possible. So use just what you need, no more than that. Minimize utilization of the interposers for active devices so that yield remains comparable, the same order of magnitude, with the yield that you may get with passive interposers. So this is the first thing to remember. We are aiming at minimally active interposers. Tomorrow we don't know, but currently this is the trend. So from the previous slide, it seems that we want to split the mini-core processor into smaller and smaller chunks. But the point is that while this results in lower cost because of higher yield, so while this translates into lowering of the cost, into an abatement of the cost, at the same time, this translates in a performance degradation. As you can see here, on the x-axis, you have the number of cores per chiplet, assuming that overall you have a budget of 64 cores. So in this case, you have 4 chiplets, and sorry, in this case, you have 4 cores, and you have overall 16 chiplets. In this case, you have 64 cores on a single chiplet. So the granularity of this integration increases as you move to the right. So you can see that the cost of the system decreases, and the cost here is related only to yield. At the same time, the average communication latency between the cores increases because as the processor is disintegrated into smaller and smaller pieces, the fragmented NoC, because the NoC becomes fragmented overall, results in more core-to-core traffic routing through the interposer. So more and more traffic flows through the interposer, which eventually becomes a performance bottleneck. And you can see it clearly here in this picture taken from the paper. So if you have a monolithic 64-core chiplet, then what you see on the interposer network on chip is just the processor memory communication. And if the topology and its load balancing strategies is carefully engineered, then the utilization of the links is pretty uniform. But if you start splitting your mini-core processor into smaller and smaller chunks, then you start introducing uneven utilization of the links, because you start adding core-to-core communication, better chiplet-to-chiplet communication to the network on interposer, in addition to processor memory traffic. And you will have a traffic peak on those links that enable direct connection between chiplets. So on these links and on these links of this different section, you will have peak bandwidth, because all the chiplet-to-chiplet traffic is aggregated there. And here the assumption of the paper, I guess, is about shared memory multiprocessor. Okay, so for the sake of cache coherence, you can go everywhere throughout your system. If you start applying a concentrated topology on your interposer, like in this case, we have a concentrated mesh, then what you can see is that you have a lower amount of resources. So this is more compatible with the minimally active interposer principle, but clearly you're putting more stress to your links because you have fewer of them. From this characterization of the environment, we derive the constraints for topology selection. A network on interposer topology should deliver low latency and high bandwidth while minimizing switch complexity, minimizing the number of switches, minimizing the wire length on the interposer. This seems trivial because everybody wants to get the highest performance while minimizing the cost, but here the cost term is especially sensitive. It's not, actually, it's an unbalanced trade-off. Here, the cost matters a lot, not only in terms of money, but also in terms of the amount, yes, primarily in terms of money, but indirectly in terms of the amount of logic that you instantiate on your interposer. The more you instantiate, the worse. So you should be able to provide very good performance while minimizing the amount of instantiated resources, while minimizing the total wire length on the interposer. Because you are adding vulnerable area, you are adding critical area. If you have a passive interposer and you're lucky, if you have a defect, the defect may fall in a wide space, in a wide region where there is no logic and there is no routing, no used routing tracks. And in this case, you know, yield is sustained. But if you keep packing a lot of logic in the interposer, this becomes an issue. Okay, so you can easily imagine that the race to find out the suitable topology for a network interposer has started. So the starting point was again the 2D mesh, again considered as a pure academic solution. And the current interest is toward the concentrated topologies. So for sure, there is going to be some form of concentration. For instance, you may want to use a concentrated mesh, as we have already seen. So you have a fewer amount of switches, fewer amount of links. Okay, so you can see here, these are the memory channels. You have also memory channels on the right. These intermediate switches are connected to the cores of the chiplets. Actually, this is a three-dimensional view. You can see here the cores in green. So assume that you have 4 cores here on this chiplet. And by means of micro bumps, these cores or their companion router, they are connected to a unique router in the network on interposer. So there is actually a degree of concentration. And you have these links that enable direct communication between the cores of one chiplet and the cores of another chiplet, and they go through the interposer. Clearly, the consideration is that if you go for a concentrated mesh, then clearly you have lower amount of resources, less vulnerable area. You have lower latency for sure, because you can, with the single, crossing a single link, you can go very far away because of the level of concentration. But you are also exposing a lower bisection bandwidth here. And now the race is toward adding bisection bandwidth to this concentrated topology baseline meshes. So let's take a concentrated mesh and let's try to improve its bisection bandwidth. Therefore, the double butterfly is a state-of-the-art solution proposed in the same paper I'm not talking about. And the goal of the double butterfly is to re-engineer the connectivity pattern in such a way that the bisection bandwidth is increased. It takes direct inspiration from the well-known butterfly topology. And you can see here the bisection bandwidth grows from 4 links to 8 links, so it's much higher. So theoretically, in principle, this topology can sustain a better peak throughput than the concentrated mesh. There are other variants though. For instance, the folded torus. The folded torus does not use like a double butterfly diagonal links. Okay, it's not using diagonal links, but it's using long range links across the X or Y dimension. So you can see here these long range links across the X and across the Y dimension, but there is no diagonal link here. Okay. And this is a similar way to improve the bisection bandwidth, because as you can count here, the number of links that are crossed by this straight line, I think it's again 8. interestingly, these topologies were carefully tuned in order not to exceed the switch degree of the concentrated mesh. So the number of switch IO port is the same, so that the operating speed is preserved, but what changes is the connectivity pattern. Okay, what changes is the connectivity pattern. And the goal, fundamentally, today in the early papers is to restore the bisection bandwidth of a concentrated topology. But new context means also new concepts. And the new concept that is being introduced in this kind of environment is the concept of misaligned topologies. So what's the problem? The problem is that if you look at this baseline realization, you can easily find out that on the interposer network, you have both memory traffic, processor memory traffic, and you have core-to-core traffic to preserve cache coherency throughout the entire system. And these two different kinds of messages end up colliding in these cross links between any two chiplets, any two neighboring chiplets. So this causes a peak of traffic on these kind of links. So the idea was to fundamentally misalign the network on interposer topology with respect to the chiplets. So in practice, the network on interposer topology has been shifted to the right. In this way, what happens is that now this switch is connected to cores that logically pertain to different chiplets. So you have two cores from one chiplet and two cores from a neighboring chiplet. And they are all aggregated onto the same router. This means that the chiplet to chiplet traffic will use its dedicated IO ports, as you can see here, while the link now is free and totally devoted to processor memory communication. So, in a sense, this technique takes pressure off the bisection links between any two neighboring chiplets, and therefore it introduces less blocking on the network. Misaligned topologies are state-of-the-art in this domain. Given that, new topologies are coming. In the same paper, the idea was to combine the pros of butterfly topologies and torus topologies. And therefore, what these people have done is to combine in a same topology both diagonal links, as you can see here. The diagonal link seems to be pretty suitable to reach a larger amount of neighboring switches, not only the ones along the X and Y dimension, but at the same time, it's using long-range links, like the folded torus. And this connectivity pattern was carefully engineered, again, not to exceed the switch degree. We don't want to introduce too many I/O ports because this is going to slow down the operating speed of the topology. And so this connectivity pattern has an inherent limitation. So the pros are that it comes with the benefits of both butterfly and folded torus topologies. But the limitation is that it has bounded switch degree. So it cannot be as richly connected as we would hope it to be. And this topology called butter donuts, well, I don't like the name. I would prefer more Italian names such as salami or ham or spaghetti and so on, but okay, I have to live with this name. This smart butter donut topology can be misaligned, like in this case, and it can actually be misaligned on the x-axis. You can see it has been shifted to the right. In this case, the shared resource between any two neighboring chiplets is the router and not the link, okay? This is a performance optimization technique. But you cannot, that's important, you cannot misalign this topology along the Y direction. And the reason is because if you misalign it along the Y direction, because Since this is a butterfly-inspired topology, you would need to instantiate 5 rows, and 5 rows are not compatible with the connectivity pattern of a butterfly. Therefore, this topology can be misaligned only along the x direction. So, if you look at the key performance indicators of this topology, we can see that it has, in general, the best indicators, key performance indicator with respect to the previous topologies. So, the butter donut, with respect to the previous topologies, it has the lowest number of nodes, which is important to match the minimally active interposer notion. It comes with not the lowest, but quite small number of links, 36. The smallest is the one of double butterfly, which is 32, actually the misaligned double butterfly. It has the smallest diameter together with other topologies. And what is the diameter? The diameter is a proxy for the worst case latency, for the worst case number of hops that you're going to go through the topology when delivering a message from a source to destination. Here in 4 network hops, you can reach all the possible destinations. The average hop count, so this is not the worst case, this is the average, is the lowest together with the folded toes, and it exhibits the highest number of bisectional links together with the together with the butter donut not misaligned. So overall, the misaligned butter donut, as you can see here, it has the best metrics overall, followed by the butter donut. So from these key performance indicators, I would say that this topology matches the minimally active interposer notion. It instantiates as few resources as possible, and it seems to come with very good performance indicators. So, deal done? Not really. There are actually some surprises, but this is also not surprising because, you know, we are just in the early days of topology analysis for networks on interposer. So here, let's characterize the load curves. So on the x-axis, you have the injection rate into the nodes of your network on interposer. And on the x-axis, you have the average packet latency. So clearly, as you increase the injection rate, you expect your average packet latency to increase. But this typically occurs in 2 steps. At first, average packet latency remains more or less constant. It grows a little bit linearly, but not too much. At a certain point, the network becomes congested, okay? And typically, this happens around a single link that becomes congestion, and congestion starts spreading from there throughout the entire network. And this happens in these knee points for each topology. And beyond that, the average packet latency skyrockets. So you can keep increasing the injection rate, but at that point, the packet latency skyrockets because clearly the network is congested. So from this load curve, you can see that the 2D mesh is, yes, a purely academic solution as usual, okay? But we said the same in the early days of network on chip. Maybe this time they are right, and I will explain you why. The concentrated mesh is better because it exhibits lower latency. You can see here lower latency, but it saturates earlier. So the peak throughput here, which is taken at this point, is lower because it has a lower bisection bandwidth. And that's the reason why we have this other bunch of topologies. And these other topologies seem to perform pretty much the same, in a similar way. So the butter donut is the best performing topology with the lowest instantiation cost. So it's a good deal. But now let's put into the picture the misaligned topology, because here we don't have any misalignment. So if you look at the misaligned topologies, we can see that there is now a dominating curve here. So there is a topology which is performing much better than the other ones. And it is not the misaligned butter donut. It's not the butter donut. It's the folded toes. Actually, if you look at the butter donut, the misaligned variant here with the dashed line it performs more or less the same as the unmisaligned variant. And for the double butterfly, if you misalign the double butterfly, you end up degrading your performance. That's incredible. So what's the reason for this strange behavior? The reason for this strange behavior is that in order to get the load curves, you assume uniform random traffic. Everybody talks to everybody, and this is the prevailing traffic, okay? And therefore, you need a topology that does not create any imbalance toward any direction. The folded torus has a similar bisection bandwidth when you travel east-west and when you travel north-south, because it's a symmetric topology. So wherever you go, the bisection bandwidth is the same, is high and is the same. But for the buttered donut, it has a very good bisection bandwidth along the east-west direction, but it has a lower bisection bandwidth along the north to south direction. And the reason is because this is inspired from the butterfly topology, which was born as a unidirectional left to right or right to left interconnection network. Therefore, butterfly derived topologies are better suited for processor to memory communication, but not for processor to processor communication. For this, the folded torus, the misaligned folded torus, performs much better. And the misalignment here seems to pay off only for this kind of symmetrical topologies and not for these fancy connectivity patterns. So let's pay attention. There is a strong sensitivity of these connectivity patterns to the traffic pattern. And also misalignment seems to be very sensitive to the connectivity, to the connectivity pattern. Nonetheless, buttered donut is still a very good trade-off because folded torus instantiates more resources, actually 25% more routers and 39% more links than buttered donuts. Therefore, if you really want to stick to the minimally active interposer notion, maybe the buttered donut is the best trade-off between the performance that you can get and the amount of resources that you instantiate on the interposer. So what's missing from this analysis? If you remember from the first part of this presentation, here, if you read the paper, there is an underlying assumption. And the assumption is that all topologies are considered to be running at the same speed. And a recent paper submitted and accepted at DAC 2020 kinds of questions this assumption, saying that the evaluation of design topologies should include modeling the operating parameters accurately, such as latency and operating speed. Therefore, the foundation of this paper is about the fact that if you characterize the maximum operating speed of these topologies, it's going to be different. No? That's the same thing that I did in the early days of network on chip design. So the 2D mesh is a topology that achieves the highest operating speed, followed by the concentrated mesh, followed by the double butterfly and buttered donuts. Unfortunately, here the folded torus is not characterized, so there is a gap in the list of characterizing topologies. Nonetheless, this is very important. These maximum speeds are based not on logic synthesis and place and route on real technology libraries. They are based on some models integrated in network on chip tools such as Descent, models that have to do with performance, have to do with power, have to do with area. Everything boils down to the accuracy of these models, but nonetheless, it's a significant step forward in the accuracy of the topology selection framework. Now, when you introduce the maximum operating speed into the game, then for the topologies under test, it is not worth reasoning about the average op count or the bisection bandwidth anymore, but it's worth reasoning about the maximum operating speed, the effective op count. So the op count not in terms of how many cycles does it take to get to the destination, but how many nanoseconds does it take to get to the destination, and the bisection bandwidth. So let's talk about megabyte per second, not about the links that are crossing the bisection cut. because these effective metrics are proxies for realistic latency latency and realistic peak throughput. So you can see that the mesh based on these models can run at 4 gigahertz as opposed to the buttered donut that can run at 2.7 gigahertz. Pretty aggressive operating speeds and technology nodes. I guess it's referred to a 22 nanometer technology node. But let's look at the key message, latency. So latency under low load is 0.9 nanosecond for the concentrated mesh, misaligned concentration mesh, and it's 0.81 for the buttered donut. So it's more or less the same. So it's not true anymore that mesh-derived topologies are bad, right? The full 2D mesh, okay, is still bad, but the concentrated mesh here has something to say because the latency is pretty much comparable. And only in terms of bisection bandwidth, so only when you operate at very high injection rates, then the buttered donut exhibits a very high peak throughput. But it's questionable whether you're going to experience high loads in the network interposer. No, this still has to be demonstrated. It also depends on the disintegration granularity of your 2.5D integrated system. So again, here there is a milder conclusion with respect to the mesh-derived topologies. So no way the C-mesh has worse zero-load latency. It's comparable to other topologies. And above all, it comes with easier routing too, because one reasons for the success of the 2D mesh in the network on chip domain was that it was enabling modular design. You instantiate processing time and an associated switch multiple times, and you get your system. Okay, so very modular design. We don't know whether this modularity consideration still holds for the silicon interposer, because I don't think that you're going to have a chiplet and a switch associated with it, no? And the ways to connect a chiplet to the network on interposer are really a lot, and there is no consolidated solution yet. So, because of these considerations, new topologies are further coming, and these topologies are the so-called kite topologies proposed in the same paper accepted at TAC 2020. This the paper is reported here, and here the consideration is the following. What was wrong in the previous topologies is the way to use long links. We should not be inspired, that's a fundamental message, we should not be inspired by pre-existing connectivity patterns. So don't start from a butterfly, okay? But reset it, start from scratch, and try to make a conscious use of long links. And if you make a conscious use of long links, then you get different connectivity patterns. And the criteria here is the following. Select a link length, a target link length, and you decide which one, depending on the operating speed that you want to get in the end. In this case, the selected link length, for instance, was a diagonal link, which is reaching one hop away from the diagonal viewpoint. And try to connect as many routers as possible with each other using this link length. And as a result, this full connectivity pattern comes out. And if you still have some unconnected I/O ports based on some predefined switch degree, use these ports for local connectivity. So if you follow this principle, more details are on the paper, you can get this kite small topology, but you can get more aggressive topologies. For instance, kite medium. In the kite medium, they use long range links, and the length is 2 physical hops that can be covered in a single network hop. But you can be even more aggressive, and you can use diagonal longer links. So you can have a link length of 2 from a diagonal viewpoint. Okay, So you can have a longer reach because of the kite large topology, but of course, the kite large topology has longer links, and therefore it's going to run at a lower operating speed. What if you try to characterize the performance of the network of these network interposer topologies? So these are the fundamental results. These are the load curves again. And you can see here that there is a dominating solution, which is kite medium. Now, we'll not go into the details, but just convey to you the key takeaway. The kite small, this topology, was not aggressive enough in the exploitation of long links. So for the technology at hand, it was making sense to use longer links than the kite small, and therefore to further minimize latency. The kite large topology uses long links too aggressively. So it uses overly long links that result in overly low operating speed, and overall it's not worth. Therefore, the best trade-off between link length, achievable operating speed, and communication latency is spanned by the kite medium topology. So we can see that the performance of a network on interposer topology is extremely sensitive to the link length and to the usage that you make of link length. Okay, we are still at the beginning of this discipline, and we can see that there are not so many papers on this topic yet. So this is an open research field. You can bring your own contribution here. You know the constraints. And let me try to summarize based on what I know of the field and my experience of the field. So what about the 2D mesh, which is mainstream on the chiplet? Is it, so to say, still mainstream also in the network on interposer domain? Probably this time not. Because the 2D mesh actually instantiates quite a large amount of resources, quite a large amount of switches and of links. And this is at odds with the notion of minimally active interposer. So I think that at least we will see some form of aggregation, okay? Aggregation misalignment seems to be a very promising direction to investigate. What about the use of topologies with long links? So here, the cost-benefit trade-offs are still unclear. And this has pretty much to do with reverting from a concentrated mesh to something more fancy. Here, the trade-offs are still not clear. We need further research. First of all, because the underlying technology substrate is not stable yet. We still don't know whether we're going to go for fully passive, minimally active, or fully active interposers in the future. We still don't know which process node we're going to use for the silicon interposer. We still don't know what is the disintegration granularity of many core processors. So we don't know, as a result, the amount of traffic and the traffic pattern. Moreover, in this context, you can notice that in this second part of the topology selection framework, it's absolutely not clear whether you can use link pipelining or not. Because the reported analysis frameworks for topologies for the networks on interposer were not considering link pipelining, okay? Actually, you may want to consider that. Actually, the link pipelining overhead depends on the baseline connectivity pattern. So there are baseline connectivity patterns that in order to pipeline them, it takes a huge area, but there are some baseline connectivity patterns that can be pipelined in the higher dimensions with minimal pipelining overhead. So it depends, everything depends on the baseline that you're trying to pipeline. So this is an unexplored research opportunity, an unexplored performance optimization opportunity. So here, you know, I think that the cost-benefit trade-offs for the usage of long links is not clear yet. But I feel like giving a recommendation. Don't design the network on interposer in isolation. Always design it for the system. Always design it in the context of a system exploration framework, because at this stage, the first goal is to converge on how a 2.5D chiplet type system at a fine granularity may look like. So questions such as what is the right disintegration granularity for many core processors are of fundamental importance. Above all, don't design the network on interposer in isolation, because isolated partial solutions are going to run out of steam very soon. But for instance, ask yourself, how can I co-design the network on interposer with the networks on chip on the chiplets? For instance, there is a recent ISCA paper, 2018, that addresses the modular design of this kind of systems. So when you design a chiplet, you fundamentally don't know in advance what will be the other chiplets of the system, okay? So you have to be ready to combine with any other kind of chiplets, and you don't even know the total system size. So you have to be modular from the ground up. And this is an issue for the routing and for battlefield routing in particular. Moreover, what is the connectivity between the chiplet and the network on interposer? Are you only connecting the boundary switches of the chiplet, or the individual switches of the chiplet are connected to the individual switches on the network on interposer? So these are all open questions. And I think that so there is a large margin to investigate on these topics, but also on utilization of this hierarchical system. So when you go from the network on interposer to the network on chip of the chiplets and the other way around, you have to go probably through some form of synchronization interfaces, because it's very difficult that you're going to distribute the same clock throughout the entire system. It's more likely that you're going to have specific clock distribution networks on the different chiplets and on the interposer. Therefore, getting out of the chiplets has a cost in terms of performance, because you have to go through the synchronization interfaces. And the synchronization cost can be as large as several cycles. So what about using, for instance, asynchronous interconnection networks in this domain? Asynchronous interconnection networks have already been used as a topology for 3D stacking by Celletti. They have a demonstrator on that. And they may be worth considering also in this domain. Moreover, you may want to distribute your traffic to the different networks dynamically. You may want dynamically to send traffic to the chiplet network on chip, or to the network interface, to the network on interposer network, right? To the network on interposer, to the network on interposer. So dynamic traffic mapping is again an option. So you can see there are plenty of opportunities to do research in this domain. Okay, I think that I'm going to stop now for 5 minutes. Let's take a break. And after the 5 minutes, I will try to answer the relevant questions that have been meanwhile posted to the Q&A section of the website. Okay, so talk to you again in roughly 5 minutes. Virtuali. 45. Okay. Let's start again. Thanks for posting your questions. And so there are many questions are very technical, and I don't think that now we have time to go into the very details of what I presented. So I selected the questions that are more general, and they are about the concepts that I presented, the strategies that I presented, and indications for the future. So the first question was about the relevance of area and performance of the network on chip for the area and performance and that power of the system as a whole. So in terms of area, typically area and power, they have a significant contribution in the high performance computing domain. In the embedded computing domain, I would say that power consumption area of the on-chip networks is negligible with respect to the metrics of the system as a whole. In the analysis that I presented at the beginning of the lecture, some topologies had quite a huge amount of area, but this area was very often associated with link pipelining. So it was associated with the intricacy of the connectivity pattern. And this leads to the key characteristics of an on-chip network, which is not only to keep to have bounded area in the HPC domain, bounded power consumption, because moving data in the HPC domain can be pretty power consuming. But once you have bounded these metrics, there are a bunch of other considerations that determine the applicability and the success of an on-chip network, especially modularity. You want to instantiate your system by instantiating the same basic time multiple times. Okay, so modularity as a way to improve design productivity, and networks on chip actually are in favor of that. They completely support that. Moreover, predictability, we'll come back to this in a while, predictability. So your post-synthesis performance is not too far away from your post-place error performance, okay? There was a tremendous predictability gap for buses before the advent of on-chip networks. So modularity, performance predictability, system-level performance, because your network on chip can also be power consuming, but maybe it enables the system as a whole, which consumes much more, to burn energy for a lower amount of time because of the high bandwidth that it delivers. Therefore, system level performance, I would say, and manageability. So you want to implement fine-grained power management in your system, and you should have network on chip support for that, because you have synchronization interfaces in your switches to decouple frequency islands. You have level shifters to enable voltage and frequency islands. So in addition to bounding area and power, which can be sensitive in specific application domain, remember that the success of a topology has to do with modularity, predictability, manageability, performance. And that's the reason why fancy connectivity patterns have never attracted system level and physical level designers too much. Second questions. Hey, you have presented a lot of fancy connectivity patterns, both on chip and on the interposer. What about routing? Some people talk about flow control. I think flow control may be not appropriate term here. Flow control has to do with back pressure, strictly speaking. But a more interesting issue concerns routing. So is it easy or difficult to route packets on a topology? And actually, in many fancy topologies, routing is not that easy because you have the problem of the deadlock. The deadlock is like in a strict system when cars block each other and nobody is able to progress anymore. This happened to me a lot of times when I had a driving license for the first time. So what about deadlock-free routing on your topology? Okay, in the 2D mesh, if you simply route in the X dimension and then in the Y dimension, that's it, problem solved. In other topologies, things are not that simple. And typically, in order to enable deadlock-free routing, you need to implement virtual channels. That is, you need to replicate buffers, for instance. And you may need special forms of flow control, such as bubble flow control. So typically, if you want to make routing on a torus deadlock-free, you need to use either virtual channels or bubble flow control. That is, in the end, network underutilization. So it's a very smart question. How difficult is that to route packets on a topology? And above all, what do you need what are the extra provisions that you need to route packets on that topology? You may need additional virtual channels, which means switch replication, buffer replication. Buffer replication is a lot of cost. Let's say up to 80% of the area and power budget of a network on chip switch is due to buffering. So let's start replicating buffering, and our cost-benefit trade-offs completely change. So this is a very smart question. This is a very smart question. Another question is about network on chip support for heterogeneous systems. So when you have CPU, GPU, accelerators, is a network on chip suitable to connect these heterogeneous blocks? The answer is yes. Currently, in high-end heterogeneous systems, you typically use several kinds of networks on chip in a hierarchical way. You have, let's say, networks on chip on GPUs or on multi-core programmable accelerators. You have network on chip at the top level of the hierarchy connecting the blocks with each other. But these networks implement at different levels of the hierarchy. They come with different characteristics. So think about a network that has to connect heterogeneous blocks with each other. So this heterogeneity that concerns the traffic pattern, the operating speed, the bit width. So this heterogeneity can be absorbed in the network interface, and you can implement communication services on top of this hardware fabric. It means that the network interface will be the fundamental adapter between the characteristics of the IP core and the characteristics of the network domain that will be selected to derive to bring the best performance in the worst case. Or you could even have the network on chip not implemented, as I've already mentioned, as as an independent island, but you can split it into islands. Therefore, you can have sections of the network on chip that have the same characteristics of the attached IP cores. In that case, you need converters on the way. You may have frequency converters on the way. You can have bit width converters on the way. And this is typical in, let's say, embedded systems or heterogeneous computing architectures in general. Last but not least, since you have these cores that have heterogeneous traffic patterns, heterogeneous even traffic requirements, performance requirements, latency requirements, what you typically do is that your network on chip should have dedicated quality of service policies to fulfill these different requirements. Okay, so you need a quality of service support in the network. You need, for instance, different virtual channels to accommodate different kinds of traffics, and virtual channel can also be a way to provide quality of service guarantees. Then clearly the things become more intricate, but if you go to the reference book that I have indicated at the beginning, all the technical details are actually there. But this is the concept. So NoCs are very suitable for heterogeneous systems because they can either absorb this heterogeneity at the boundary or they can implement converters on the way. Another consideration was, hey, why not using a fully connected topology to connect the chiplets with each other, since we don't have a lot of chiplets for the time being. And I would like to say that this is a smart idea. There is still a lot of room to investigate these kind of possibilities, but clearly everything has to do with how many cores of the chiplet you connect to the network on interposer. Because if you want to connect all the cores of the network on interposer to a corresponding switch in all the cores of the chiplets to the corresponding switches on the network on interposer, it's one story. If you have a single input-output port for the chiplet on the network on interposer, it's a different story. So you need to fix before the connectivity requirements, because before being able to project the target topology. But full connectivity seems to be, for the time being, a promising direction if the granularity of this chipletization remains not too aggressive. Also considering that if you are using a mesh or even for the other topologies on the network on interposer, fundamentally, once a packet has been injected there, then most of the network will appear to the injector as an indirect network. Think about it. So what is the difference between direct and indirect network? So direct network is a network where every communication actor is attached to a different switch. An indirect network is, such as a multi-stage interconnection network, is a network where the injector is attached to a switch, and then you have other switches that are not connected to any other communication actor, but are just there for the purpose of segmenting the path to the destination. This is called an indirect network. So consider that you are injecting a packet from a chiplet into the interposer network. Clearly, since that packet has been injected there, that packet doesn't want to go to a core of the same chip, clearly, but it wants to go to a core of a different chiplet. Therefore, all the intermediate switches to get out of the chiplet area, they are indirect switches, right? Because they are not candidates for destinations. So, you know, there are some observations, and some of you are observing, in my opinion, the right direction, and still lots of degrees of freedom for further investigation in this domain. Another question is how to assess at the first glance whether a topology design is feasible or not. Well, you have some proxies. Some proxies have to do with, let's say, latency proxy is the diameter. So the worst case number of hops to get to the destination. Another proxy for throughput is the bisection bandwidth, as I demonstrated. You split the network into two symmetric parts, and the the number of links that have been split, they represent the bisection cut, and they are a proxy for the peak throughput that the network can sustain. But these are kind of abstract metrics. They are proxies. There are, I think I introduced it today, two other metrics that you should consider from the ground up, not as an afterthought, which are the number of input-output ports of your switches. Because, as I have demonstrated in this lecture, the number of switch I/O port decreases significantly with the maximum operating speed decreases significantly as you increase the number of input-output ports, okay? So the number of input-output ports, this has a fundamental impact over the maximum operating speed of the topology as a whole. Also, you should take a look at the link length, okay? Because the link length is probably, for long links, the critical path to the topology as a whole. And these are the locations that you may want to invest on link pipelining and so on. So I think whenever I look at the topology, I look at these four main aspects. Okay, there are others, but have lower importance, in my opinion. And these aspects actually tell you at a glance how this topology is going to look like. You may also look at the connectivity pattern, if it is intricate or not. If you consider, for instance, a fat tree, no? We try to lay out a fat tree in the early days of NoC, and it's a mess. It's completely a mess, because in these cases, you can see, many times you can see a smart connectivity pattern, but it is difficult to draw it in a piece of paper. When it is difficult to draw it in a piece of paper, you start having a lot of crossings, right? Then it means that it will be difficult to lay out on the chip surface. So at a glance, I think it's pretty much feasible to understand if a topology is promising or not. And I don't know if I will have time, but I will try to provide you in the last lecture an example about how these considerations also hold for an optical network on chip. More or less exactly the same considerations, but in a different environment. Last but not least, I can assure you that this material has already been posted in the website of the summer school, and also the recording will be made available. Okay, now it's pretty late, so the idea is to cover some of this material in the next lectures, but I would like to dedicate the last, let's say, 15 minutes, since I've already taken these minutes for the Q&A session, to provide a few other technical details. And I would like to, let's say, skip this. I will go back to this next time. And I want to actually start from here, okay? So, because another lesson that we learned in the early days of on-chip interconnection networks was derived by directly comparing a network on chip with the buses that were state-of-the-art at that time. We're talking about 2007 here. And there were state-of-the-art buses that are still state-of-the-art in many system on chips. They are multi-layer buses. So we have, like in this case, 5 shared buses that are following the de facto industry standard called AMBA AHB from ARM. The specification comes from ARM. And then you have, in order to connect these layers with each other and with global main memories, you have a top layer, which is nothing else but a crossbar that follows the standard AMBA AHB protocol. And we compare this with a network on chip. It was a quasi-mesh topology, quasi-mesh in the sense that you had concentration of 2 cores onto the same switch, okay? And the comparison was performed on a 130 nanometer UMC technology library. So even though the process node is quite old, the considerations are very important, and especially today, and I will try to demonstrate it why. So what we got out of this comparison was that if you look at the operating frequency and you compare the post-synthesis operating frequency with the post-place and route operating frequency, the network on chip, we here have 21-bit network on chip and 38-bit network on chip, so providing more throughput, was much more predictable from a performance viewpoint than a number multi-layer. And the reason is because here you have path segmentation, so very controlled path timing throughout the entire communication architecture. While the multi-layer AHB was a fully distributed combinational logic throughout the chip, therefore it was not very much predictable. So you have a large, significant performance drop when you go to pre-layout to post-layout analysis. In terms of bandwidth, this is an excellent news again, because the network on chip is providing a huge amount of bandwidth with respect to state-of-the-art buses, okay, regardless of the specific numbers that may appear old, but no, the provided bandwidth is much, much higher than a high-end multi-layer bus. And I would like to stress again that today in real systems, you may find these architectures together. You may find a network on chip in some specific accelerators or at the top level of the hierarchy, and in some other portion of the chip, you may have this kind of structure. Area, here, we have the bad news, in the sense that if you only look at interconnect area, network on chip came with more area than a multi-layer AHB. Roughly in the same years, there was a white paper from a company demonstrating that the network on chip also comes with lower area with respect to the multi-layer bus, but clearly this depends on the kind of topology that you are instantiating. It depends on the target system. So actually, if you want to look at this from a purely scientific viewpoint, in the early days, that was the ground truth. Then, of course, there were a number of optimizations, and probably today that's true, that the numbers have been reversed. But at the beginning, this was a situation, and I would like to tell you the importance of this beginning later. Let's look at another bad news in the early days. So if you look at the power consumption of the network on chip, the power consumption was actually higher. So we had 1 order of magnitude higher power consumption with respect to a multi-layer AHB. And this is a very accurate analysis because these are post-layout numbers, okay? And the main reason for that was that, the network on chip implements a lot of buffering, and the buffering accounts for roughly 80% of the total network on chip power. So the consideration is that the industrial uptake of NoCs took its steps from these contradicting numbers from research, okay? So you may argue that they did better, maybe, I don't know, not sure, depends on the system, but that was the ground truth at that time. There were a number of optimizations. But this is important because today we see exactly the same thing for emerging interconnect technologies. We can see that today the most promising emerging interconnect technologies come with larger power consumption. They are analyzed because they are advertised as low power interconnect technologies, but in the end they are not truly low power. They consume actually a lot of power, in my opinion. And the benefit is a different one. Where is the benefit? Well, let's still keep learning from the early days. In the early days, we saw this kind of benefits, okay? This is before any kind of optimization that you may think of about your chip interconnection network. And the benefits was measured at the system level. Because when you run an image processing benchmark for 1 millisecond on the multi-layer bus, the same benchmark takes a lower amount of time to execute on a network on chip because of the higher bandwidth and because of the lower latency of many transactions. So this means that if you start measuring the energy of the fabric, things are still pretty much unbalanced. But when you consider the power of the system as a whole, you start seeing the benefits that the network chip brings you. Because, okay, if you consider a 1 watt system, then the power consumption of the systems are comparable. But if you start considering a 5 watt system, then the network on chip starts bringing benefits, okay? And since these kind of topologies are used for general purpose system that typically consumes much more than this, the network on chip can clearly bring you system level energy savings. The same savings can be achieved in different contexts to different techniques, as we will see shortly afterwards. So remember this is a very key takeaway. The key takeaway is that, you know, you don't have to look just at a communication fabric in itself in an isolated way. You need to look at the benefit that this brings to the system as a whole. And in the early days, networks on chip, in addition to modularity, predictability, manageability, they were bringing system level performance speedups and system level energy savings. What about other domains such as the embedded computing domain? In the embedded computing domain, there has been an aggressive optimization of networks on chip, especially from the topology viewpoint. Because in this domain, typically applications are known well in advance. They are known at design time. Therefore, since they are known at design time, you know the average communication bandwidth between any two cores of an application. You know this kind of plots. They are called the core graph representation of an application. You know average communication bandwidth. Therefore, the idea is to customize a topology for this kind of traffic pattern, because typically it is known in advance. And customization is a huge source of power optimization and performance optimization, both of them. But in this domain, there is a very important consideration. In the domain of the application-specific networks on chip, what is the true intellectual property? The architecture? No. So let's try to give the answer. This kind of irregular topologies, they use heterogeneous M by M switches, such as they instantiate a 3x3 and 7x7 switch in the same topology. They use even 2x3 or 7x1 switches. They need to solve routing congestion issues, serious routing congestion issues. They need to deliver link performance predictability, and link length is not the same throughout the topology. You may have links of different length. Therefore, you need the performance predictability. You need first-time right design, despite the topology regularity. In this situation, you have blurred boundaries between front-end design steps and back-end design steps, because many times you may want to deal with the back-end issues ahead in the design methodology. For instance, you may want to think about routing congestion early in the topology synthesis. You may want to think about higher drops early during topology synthesis. You may want to think about expected link length early during topology synthesis. So in this context, the true intellectual property is not the architecture. Everybody today can build his own network on chip architecture, more or less. But the true intellectual property in this domain is the synthesis tool flow. I had the chance to follow the onset of a spin-off in the network on chip domain. At the beginning, they thought the true IP was the architecture, but very soon they realized that the true IP was the automatic synthesis tool flow for the application-specific topology. And that's the reason why the IP of this spin-off has been recently acquired by a major network on chip vendor, Arteris. In this way, all the algorithms, the synthesis methodologies of customized topologies have been acquired by a major network-on-chip vendor nowadays. And that's the reason why we have extensively investigated on an advanced framework for topology synthesis. Maybe you want to start, this is the outcome of a European project called NoC, involving many NoC vendors and either major companies such as Infineon. At the time there was also Atlantic, Teclatec, Inox, and so on. So you start from core graph representation. Then, very early in the synthesis methodology, you may want to reason about floor planning. You may want to have a rough floor planning, a rough estimate of the floor planning of your system. In this way, you can try to understand what is the communication bandwidth between any two neighboring cores, and you may want to draw a thick lines that is as thick as the amount of communication bandwidth between the cores. So here we have a thick line that spans quite large length. It means that you have a lot of traffic which is brought around throughout a large chip surface, which doesn't hold promise of low power. So you may want to optimize it here, and at the same time, at the floor planning stage, you may want to optimize higher drop. You can have an early phase higher drop analysis. Then you can come out for a customized topology like this for the connectivity, for the traffic scenario at hand, and for the floor plan at hand. You can also generate floor planning directives for the back-end synthesis steps. And once you have the customized topology and floor planning directives, you can start the back-end synthesis, place, and route, and you can end up with physical convergence. Here, the color blocks are the switches and the network interfaces and the pipeline stages of this customized interconnection network. And here you can verify whether your early stage analysis in terms of performance predictability, power, or higher drop was accurate or not. And actually this flow was tuned in order to have accurate early stage analysis within 10% of accuracy of post place and route results. This is actually a validation of the early phase power analysis that took place here and sign off. And you can see that for several use cases, multimedia use cases, the early phase analysis was pretty much accurate. So what should we learn from this? We should learn from this that customization is important for power efficiency, but above all, we should learn that synthesis tool flows in many cases may be the true intellectual property. And in the next lectures, I will demonstrate you that similar considerations apply today. Because today we have a different problem, and the different problem is to cross-benchmark electronic networks on chip with emerging interconnect technologies, right? So it's no more a matter of cross-benchmarking networks on chip against multi-layer buses, but it's a matter of cross-benchmarking silicon nanophotonic networks against electronics networks on chip. And in fact, at the horizon, we can see that silicon photonics is really gaining momentum. And beginning from 2018, mega data center and HPC companies have really triggered the silicon photonic markets because they have planned for the extensive deployment of silicon photonics interconnects in upcoming hardware renovation cycles. And by the way, optics has made a long way of penetrating deeper into smaller and smaller scale systems. So optics started from transoceanic links, and today we find silicon photonics in the rack, at the board level, and it's also possible to envision that at the level of the silicon chip. Then today the actual source of debate is whether silicon photonics is going to make it all the way to the silicon chip. But what are the fundamental messages to conclude this lecture? That, let me skip this. When we try to cross-benchmark an optical network on chip with an electronic network on chip, we find similar results to the earliest cross-benchmarking frameworks of networks on chip as opposed to multi-layer buses. In this 4x4 system running at 1.2 gigahertz, 32-bit of parallelism implementing a directory-based implementation of the NoC protocol, if you implement electronic network on chip from layout to the architecture to the network interface, and you compare it with an optical network on chip. Now, I don't want to go into the details. Details here are not important. The important here is the message. And you do that with the same level of accuracy, layout, topology, optical ring, network interface to drive the optical network on chip. And you look at the performance results for the parsec benchmark suit, you can see here that the network on chip with 3 bits of parallelism and 4 bits of parallelism, it's currently, it depends on actually on the protocol, but with the simulated protocol here, which is a wavelength routed protocol, it's not possible to have the same level of parallelism of electronics. You can have a lower level of parallelism, but you can send bits at a much higher speed at more than 10 gigabit per second. So you can see that the execution time is lower. How much lower? With 3 bits of parallelism in optics, it's roughly 18% on average, and it's 23% at 4 bits. So in some cases, for some applications such as can mill and swap options, it's roughly 30%. And this is not a communication intensive system. So here we are just simulating cache coherence traffic. But when you look at energy consumption of only the buses, of only the network, sorry, you can see that the first column is the electronic network on chip. And the electronic network on chip consumes less energy than optical network on chip solutions. Because in the optical network on chip, and this is using aggressive parameters of the optical technology, parameters that probably are not possible today. For instance, this is assuming 20% wall plug laser efficiency, okay, which is really a lot. And in telecom application, the wall plug laser efficiency is a few percent, not 20%. So here we are assuming 20% wall plug laser efficiency, other optimistic parameters for optics. And when you sum up the overhead of the network and the overhead of the network interface, the conclusion is that even in the best case, optics consumes more power than electronics, although this is advertised to be a low power signaling technology. And I think that many people nowadays in the community agree on this. This is not a low power technology at all for chip level networking, okay? So what's the point? Well, the point is that we should not focus too much on the interconnect. Lesson learned from the early days of network and chip design. Let's focus on the system level. And the Tilera GX processor that has been considered here burns on average 15 watts. So let's display here total system energy. Total system energy for electronic network. This is a normalized one. For the optical network with conservative parameters and with aggressive parameters, with 3 or 4 bits of parallelism. Let's just look at 4 bits of parallelism. You can see that from the total system energy viewpoint, optics brings you 21% savings, and only 24% savings if you consider aggressively optimized optics. Why? The reason is simple. Because the power consumption of the system as a whole depends mainly on the processor cores in this system and not so much on the interconnect itself. So what in this system you are asking to the interconnect is mainly performance. And if you can provide, let's say roughly 20% performance in these use cases, we can translate this into roughly 20–25% total energy savings. What about further optimizing the maturity of the interconnect technology? Well, doesn't bring you a lot. So rather than investing on that, remember that an interconnection fabric speeds up application execution and causes, for this reason, the system to burn less energy for that. Therefore, please invest on improving bandwidth efficiency. So please instantiate networks that, with respect to this experiment, can provide more gigabyte per second, approaching terabyte per second. Also, since the optical network on chip is dominated by laser power, which is a static power contribution, please find some way of gating optical power, similar to clock gating in VLSI design. Please improve laser power efficiency, or improve other things that now maybe don't make sense to you because we haven't gone into the details. But another thing that you may easily understand, why not customizing the optical network on chip similar to what we have done in the electronic domain for application-specific networks on chip? Actually, this depends on the application domain, it's true. But some form of customization, even in general purpose system, is affordable. Okay, that's the message. So today the history is kind of repeating, right? And it's kind of repeating, and we still see that the interconnecting itself is not a power, but it enables the system as a whole to be low energy. And the real conclusion is that for the time being, such savings are still not enough. So it's tough to convince a company to invest money on this technology, which is very expensive because it's a disruptive technology, and just getting 20% savings. We need more. And that's the real conclusion. And in order to get there, this is the last slide, to get there, this is the last slide, you need to invest also on design automation, similar to electronic network on chip. So it's not only a matter of technology maturity, but also design automation. Why? Because today, system designers are here and technology developers are here. And in the middle, there is a huge gap. There is a huge gap in the middle. So system level designers don't have the models and the tools and the methodologies to do system level design with the emerging technology. Therefore, it's not currently possible to answer the following question. How can I synthesize the most efficient optical network on chip solution for the requirements of the connectivity problem at hand? How to enforce technology-aware decision-making at each layer of the design process? That's not possible. That's not possible because the way to answer this question is to invest in design automation. And that's why a new discipline is coming out, and that's pretty exciting, which is design automation for emerging technologies. And you find in this slide a few pointers to my research activity on this exciting field. The goal is to try to set up similar synthesis and refinement flows for optical interconnection network, similar to what you did for electronic networks on chip, similar to what you do for any normal VLSI design flow. You start from abstraction, from a high-level specification, and then you refine it to a technology-independent gate-level netlist going through the RTL description. And then you map this onto a technology library, and you come up with planar geometric shapes. We need something similar for optical networks on chip, and this flow is not there yet. And if you don't get there, there's no way you can provide system-level designers the tools to do system-level design with the emerging technology. So we will cover some of the remaining material in the next lecture. This is just to anticipate you what will be the topic of the next lecture. Okay, the topic of the next lecture will be networks on chip for the fog computing domain. So network on chip for data-intensive, context-aware devices and services that use Internet of Things data to perceive, model, and adapt to their environment and use it. So it will be an interesting and exciting case study about how to design your network on chip for the Internet of Things domain, and in particular for fog computing platform. Thanks for attending this lecture and talk to you on Friday. Bye-bye.